special case of this inequality we're going to be using today. It's called the AM-GM Inequality. It stands for arithmetic mean, geometric mean. And so it's a result that holds for all natural numbers. I'm just going to prove a very simple case of it for n equals 2. That's when we have two variables. Now I'm going to start out with we'll use x and y, the standard variables. So square root of x, I think we need minus here. Yeah, minus the square root of y. And of course, we're assuming x and y are positive. All right, quantity squared. All right. Now, when you perform the squaring here, you certainly get. Now notice, oh, by the way, this is greater than 0, right? So let me write that down. It'll be a little sloppy here. That's greater than 0, okay? But it's also equal to x minus 2 root x. 2 root xy, excuse me. Plus y. Now, of course, that's still greater than 0, right? Now, notice what happens right here. Again, y'all, this quantity, this number squared has to be greater than, I should put greater than or equal to 0. Okay? Now, notice what happens here, and I'll just write down the result. When you bring this to the other side and divide by 2, you get x plus y. You get x plus y divided by 2. Okay, is greater than or equal to the square root of the product. So you see what's kind of neat about this simple looking result is it's an inequality that relates addition and multiplication. Okay, so again, this is a proof of the two variable case, n equals 2. We're using the letters x and y. Very, very straightforward. And notice that this result here, x plus y over 2, is exactly in this form for n equals 2. Y'all, this pi notation just means product. You're taking the product rather than the sum. Pi notation means you juxtapose and multiply all these guys together, okay? And so there's a nice symmetry, or whatever you want to call it, duality. You're dividing by n right here, and then you're taking the nth root of n right here. This is the geometric mean. This is the arithmetic mean for n variables, okay? Now, the rest of this is very straightforward. We have this initial condition here. It's all the possible two products of 4 variables right here, basically, all right? There's 6 of them. That's 4 choose 2 for you combinatorics people. 4 choose 2, there are 6 of them. And it's given that all these pairs, possible pairs of A, B, C, and D add up. Their product add up to 3 exactly, okay? Now, that gives us an enormous... The rest of this is straightforward. It really is. Notice this is just a direct handoff. Right here, you're literally just putting everything where it belongs, right? So this very first line is clear. Now let's keep on going right here. Now right here, if you take a look at this piece right here, you do see where this came from, right? You have 1, 2, 3 A's, so there's A cubed. You have 1, 2, 3 B's, and so on. So by the commutativity law, you can put them all together as A cubed, B cubed, C cubed, D cubed. But notice this is kind of nice also, because let me come off to the side here a little bit. I may not have given myself enough room here, but you can write this as, okay, the 6th root, right? The 6th root of just the product ABC, okay? So I'll write this down, ABC, D. Y'all, it's supposed to read ABCD. Let me envelop that in parentheses. Quantity cubed, right? But if we write this in the more familiar rational exponent notation, 3 over 6 is 1/2, right? So we can write this as ABCD and let me make this raised to the 1/2 power. Okay. Y'all, what is that? Well, the square root symbol gets used so much that the 1 and the 2 get left off, but this whole product is something raised to the 1st power, and of course we have a 2 right there, right? So anyway, you probably didn't need to see that, but anyway, I like showing the algebra here. It's just laws of exponents combined with using the AM-GM inequality. All right, now the rest of it's very, very, very straightforward here. Now remember that A plus B, all of this stuff, I won't say it is equal to 3, right? All these, the product of the variables and pairs is equal to 3. And so notice that's exactly what happened right here. We squared both sides. If you square this, this is equal to 3 by the initial condition, right? It's equal to 3 by the initial condition. And so right here, that's where the 3 squared ends up. Here you square the right-hand side, 6 squared is 36, and the radical goes poof, right? And so at this stage, we have 9 over 36. 9 over 36 is going to be an upper bound for the product of all the variables. Okay, but of course this is equal to 1/4, right? So 1/4 is the answer. 1/4 is the answer we're looking for. Now, yeah, there's more I can say. We've already proven what we set out to prove. 1/4 is our upper bound. That is the answer to the problem. We did ask for an upper bound of AB, the least upper bound for ABCD. There's certainly nothing smaller based on this inequality, so it is the least upper bound. Now, something else that's rather interesting here. Let's see if I have room to show you this. You can think of right up here the equality condition, and that's one of the results of the AM-GM inequality. The equality condition happens exactly when all these objects are equal to each other. So in other words, when this 1/2, notice that 1/2 plus 1/2, okay, and so on, plus 1/2 right here. That's 6 of them, right? All of these 6 1/2s add up to 3, right? But notice that if you, I think I got room here. Let's just use CD for example. This would right here would imply that C equals to D, and the same for the other variables. Equals to 1 over root 2, right, folks? 1 over root 2 times 1 over root 2 is 1/2, right? So the equality condition actually occurs when A, B, C, and D are equal to 1/2. If you need, that's not what we call for, but that's the equality condition for the arithmetic mean geometric mean inequality. But in any event, let's move back down here. Here's the solution. I hope you enjoyed it.